Hey class, Mr. Durst here, and we are going to dive into connective tissues today with this recording. When we think of a connective tissue, there's a lot of different ways to slice and dice this category. It's a very diverse category. I need to emphasize it's diverse here. So I'm going to circle that there. There we go. It's very diverse. But generally speaking, when we think of connective tissues, a good kind of general guideline is that when you look at the volume of the tissue, the cells typically are going to occupy less than 50% of the overall volume. Another way of saying is that the matrix of the tissue is going to be greater in volume than the cells of the tissue. So as we look at these connective tissue cells, most of the cells are not going to be typically touching each other. They're not going to be in direct contact with each other. As we think of functions of connective tissue, it's going to be kind of your support tissue. I like to think of it as the filler or the glue tissue. It's all over our body. It also helps to serve to protect organs, in particular when we think of the adipose and skeletal tissues that can cushion and encapsulate organs to help protect them. And there's a lot of variable vascularity. When we think of vascularity, I want you to think of the amount of blood vessels. So if we look at loose connective tissues, oh man, there's a ton of blood vessels. And that's why when you get a paper cut, it just bleeds and bleeds and bleeds, even if it's not that big of a cut. But then there are other kinds of connective tissues, such as cartilage, that has almost no blood vessels in it. And that's, both good and bad. I mean, it's good in that we're not constantly bleeding from our knees whenever we jump up and down or do, run up the stairs. But on the flip side, it also means that if we damage our cartilage, it takes a very long time to heal from those injuries because there's very low nutrient delivery rates. So let's look at some functions in more detail. Connective tissues will connect organs, as the namesake implies. In particular, connective tissues make up tendons and ligaments within our bodies. We also get support in terms of bones and cartilage. Connective tissues will come as physical protection. We have our rib cage, we have our cranium, our skull to protect our brain, our rib cage to protect our lungs and our heart. We also are going to get immune protection. Blood is a connective tissue, and we have white blood cells that are part of that connective tissue. We also use connective tissue for movement. In particular, our bones are going to give us leverage. When our muscles contract, those muscles will pull on tendons and ligaments, or particularly tendons, which will then transfer the force to bones, and then that force can go from one bone to another bone via a ligament. So there's lots of movement associated with our connective tissues. We store things with connective tissues. We store energy with fat. We store calcium and phosphorus in the extracellular matrix of compact bone tissue. We can also generate heat with our connective tissues. Brown fat, in particular, in newborn infants, is a fabulous source of heat production. I remember taking my oldest son camping, and he was, I want to say 6 weeks old at the time, maybe 5 weeks old at the time. And it was late October, early November, and there's frost on the ground outside. And then, it's just starting to snow. And we were my wife and I were in the tent with him. And oh my gosh, that guy was just a little furnace. He was in the sleeping bag between us, and he just pumped out heat. Little kids, little infants with their brown fat, they pump out lots of heat. And then finally, when we think of blood is used to transport nutrients throughout our bodies. Now, of the connective tissues we're going to focus on first, it's going to be fibrous. And our fibrous connective tissues are going to have lots of fibroblasts. When we think of a blast, I want you to think of a cell that builds stuff. What does this building cell build? It builds fibers. And of the fibers that fibroblasts build, the most common is going to be collagen fibers. But there's some other fibers in the extracellular matrix as well. There's elastin, and there's also going to be reticular fibers, but the fibroblasts primarily are going to make lots and lots of collagen fibers. We're also going to have macrophages within our extracellular matrix. Macro means big, phage means eat. A macrophage is that literally big eater. It's a cell that a white blood cell, a leukocyte, that roams around the extracellular matrix and will phagocytize or swallow things that don't belong there. And our macrophages will come from a different kind of leukocyte known as a monocyte. So monocytes lead to those macrophages. As we think of leukocytes, there's just a lot of general leukocytes in the extracellular matrix of our connective tissues. We have neutrophils, which are the most common kind of leukocyte, and neutrophils are known for primarily focusing on attacking bacteria. We also have a lot of lymphocytes, and those lymphocytes can focus on attacking bacteria and or recognizing toxins or destroying human cells that have an intracellular pathogen. So maybe a virus that's infecting a human cell. We also are going to have a lot of plasma cells in our extracellular matrix. Plasma cells are the antibody builders. These are the cells that secrete antibodies in our bloodstream or in our body. And the reason they're known as plasma cells is because they are initially isolated from blood plasma. We also can have mast cells. And when we think of a mast cell, I want you to think as a cell that can inhibit clotting or dilate blood vessels. So this is a cell that is involved in some of the inflammatory responses in our body. And if we have an allergic reaction, it's oftentimes linked to a mast cell gone wild or a mast cell that's run amok. And these cells are secreting too much heparin, too much histamine, and it's causing too much of an inflammation response. And then we have the adipocytes, or as I like to say it, I'll admit I personally say it as adipocyte. These are the fat storage cells. They store triglycerides in a large storage vacuole within the center of their cell. So here's a figure showing these things that we just talked about. We have the adipocyte, we have the mast cell, we have the neutrophils, the lymphocytes. Look at this elongated fibroblast here, and then this really large macrophage. And then for the fibers, those fibers made by the fibroblasts, we have collagen fibers. I'm going to really emphasize the one. It's a big one, but we also have a lot of elastic and reticular fibers, depending on the particular connective tissue which we are looking at. So of those fibers, collagen fibers or collagenous fibers are the most abundant. It's about 25% of our body's protein content. And because our dry mass is about 50% protein, you can think of it like this, our dry mass of our body is going to be about 12% collagen. So 12% of the solids in our body is just collagen fiber. It's super common. It's very tough, flexible, and stretch resistant. It makes up tendons and ligaments. We have a lot of it within our skin. We also are going to have some in the extracellular matrix of our bone and cartilage, but it's a different kind of collagen. It's not as easily visible within photomicrographs. We also have a lot of reticular fibers, and these fibers are going to be coated with glycoproteins that cause them to be kind of, lack of a better term, sticky and branched. And we'll have lots of reticular fibers in both the spleen and the lymph nodes of our bodies. These reticular fibers allow for us to filter fluids. You can think of the reticular fibers as the fibers of a net that filter the liquid flowing through the net. We also have a lot of elastic fibers. And as the name implies, they are stretchy. They allow for stretch and recoil. The protein the elastic fibers that are made out of is called elastin. And these elastic fibers are thinner than collagen fibers and about the same thickness as the reticular fibers. It's just the orientation is a little bit different as we look at them. Now, as we look at, I think I went too far here. Give me a moment. All right, nope, I didn't skip anything. Okay, good. So as we look at our connective tissues, we have a lot of ground substance in our connective tissues. Ground substance is the fluid component of the extracellular matrix. And a lot of times it's gelatinous or rubbery. The reason for that is because it has a lot of glycosaminoglycans, or GAGs for short. Glycosaminoglycans is a little bit of a tongue twister. It's a mouthful. And as we look at these glycosaminoglycans, just really big pieces of carbohydrates that have some amino acids and some uronic acids attached to them. You can effectively think of these as a molecular sponge. So the purpose of this molecule is just to suck up water. So as we look at these glycosaminoglycans, they regulate water balance. And by regulating water balance, they will also automatically regulate electrolyte concentrations, because as you change the water content, you change the dissolved content concentration of those cells. Of all the glycosaminoglycans, chondroitin sulfate is by far the most common, and it gives a lot of stiffness to our cartilages. We're also going to find that heparin and hyaluronic acid are also some other examples of GAGs, but I just really want to draw a lot of attention to chondroitin sulfate. That is by far the most common glycosaminoglycan. Now, as we look at our loose connective tissues, they have lots of ground substance, lots and lots of liquid between their cells. There's a lot of space between the cells. The two most common, or the two most notable, I should say, are areolar tissues and reticular tissues. We also have dense connective tissues, and as the name implies, instead of being loose and having a lot of free space, they are dense and do not have a lot of ground substance. Instead, they have a lot of extracellular fibers filling up the space between the cells. And depending on our fiber orientation, it's going to change what kind of dense connective tissue we're working with. We have dense regular and dense irregular connective tissues. When you think of a dense regular connective tissue, I want you to think of a fiber orientation where the fibers are all roughly parallel with each other. And I'll switch colors here. And if you think of a dense irregular connective tissue, I want you to think of a tissue where the collagen fibers are irregularly oriented to each other. It's kind of a hot mess. It looks a little bit like hamburger, for lack of a better analogy. Ooh, I did not want to click that button. Clear. There we go. So as we look at that areolar tissue, it's a very common connective tissue. It's, in my mind, it's kind of like the default glue in our body. It's going to be nestled and wedged in between a lot of different organs to help anchor membranes and organs to each other. And as we look at these areolar tissues, they have all of those 6 cell types that we talked about earlier in this presentation, and the fibers are going to be randomly oriented. And all of those randomly oriented fibers, most of them will be collagen. We have small amounts of elastic and reticular fibers also. I want to just draw some attention to the fact that the fibers are randomly oriented. A random orientation to the fibers gives areolar tissue about equal strength in any given direction. So you can tug on it, you can pull it up, you can pull it down, you can pull it to the left, pull it to the right. You'll have about equal strength if you pull it in any direction, apply force in any direction, because the fibers are oriented in all directions. So we find this fiber in almost every part of the body surrounding stuff. It's kind of that, like I said, the glue that holds things together. Nearly every single epithelium in our body will rest on an areolar tissue as a bed or an interface to the underlying substrates. We find that within our areolar tissues, they have lots of blood vessels that are highly vascularized, and they're also going to have lots of white blood cells actively patrolling them. So because we have areolar tissues all over our bodies, and that those areolar tissues have lots of leukocytes, we in effect have white blood cells, leukocytes, roaming our bodies, constantly trying to get ready to fight off infection. Here's a classic looking photomicrograph of some areolar tissue, and here's that same photomicrograph with the contrast emphasized and a little bit of Photoshop magic to make the differences between structures a little bit more noticeable. And I want to emphasize loosely organized fibers, lots of blood vessels, and then you can see lots of individual nuclei as these dark circles. Let me switch to green here. As these dark circles that I'm highlighting green, because we have lots of cells. We have the fibroblasts, the leukocytes, so on and so forth. In this figure, all cells are stained the same color, so we really can't differentiate one cell type from another cell type. As we look at reticular tissues are going to have mostly reticular fibers and a lot of fibroblasts. As we look at the reticular fibers, those reticular fibers are going to form lots of channels and passageways so that we can have lots of filtration. We typically will find reticular tissues in lymphatic organs. Lymphatic organs are primarily going to serve to filter lymphatic fluid in our bodies and then remove pathogens and antigens from that lymphatic fluid and expose that to the leukocytes, or the white blood cells that are waiting in our reticular tissues to be exposed to any of those potential pathogens which may be present. So we find lots of reticular tissues in lymph nodes, the spleen, the thymus, and to a lesser extent, the bone marrow, in particular the red bone marrow. We also have dense regular connective tissues. And as we look at this dense regular connective tissue, I want to just really emphasize here the wavy, nearly parallel, or nearly, parallel is the word I'm looking for, not perpendicular, nearly parallel orientation of the collagen fibers within the extracellular matrix. But you can also see dark splotches, and those dark splotches represent individual nuclei from the fibroblasts. And as we look at this tissue type, mostly what you're going to see is just collagen fibers. There are lots of collagen fibers. And the collagen fibers don't leave a lot of leftover room for the fibroblast. And what you end up seeing is a compressed nuclei with the fibroblast that is elongated in appearance. We use dense regular connective tissues to make tendons, attached to muscles, and ligaments, which attach to our bone interactions, or connect bones to bones. We also have dense irregular connective tissue. So in this instance, the collagen fibers are oriented in many different directions all at the same time. And they're going to be very densely packed. And because these fibers are so randomly organized, the tissue can withstand a lot of unpredictable stress, which is another way of saying that it can resist tension from any given direction. It's really good at resisting pulling, tugging, twisting forces. We typically find dense irregular connective tissues forming protective capsules around individual organs or within the dermis of the skin, the dermis of our skin being the deep layer of our skin. We also have a lot of adipose tissue in our bodies. And as we look at this adipose tissue, unfortunately, I have more of this in my body than I wish I did. You can just think of it as fat. And for most individuals, when we think of fat or adipose tissue, it's going to be the yellow adipose tissue, not the brown adipose tissue that we associate with infants. And we're going to use it as a storage reservoir. Excuse me. We're going to store fat in the fat cells, or the adipocytes. And we're going to store energy in very highly dense fashion. One of the wonderful things about triglycerides is that we get almost, or actually over double the energy storage capacity compared to carbohydrates and proteins. We're constantly making new triglycerides and digesting old triglycerides. This is a constant process within our bodies. So, what I mentioned earlier, we have white fat and the yellow fat, white fat, sometimes referred to as yellow fat, and then the brown fat. So, as we look at this white fat, it's going to be adult fat. And as we look at the photomicrographs, it can look like chicken wire to some people. I'm going to go ahead and advance a slide here. So, this is our adipose tissue, our white fat that I was mentioning. I'll go back a slide now. And we use this white fat for insulation. We use it for energy storage. We use it for cushions. And it also is going to give us a lot of the contours of our body. So the adult female breast and adult female hips, or I should say the post-pubescent female breast and post-pubescent female hips, are going to have increased amounts of white fat in them. When we think of that brown fat, the brown coloration of this tissue comes from a high blood vessel concentration and lots of mitochondria that are present. And these mitochondria are constantly chugging through the fat, turning it into ATP, giving off lots of heat in the process. So brown fat is your heat generation variation, or heat generating variation of adipose tissue. Here's what this adipose tissue looks like in a photomicrograph. I want to emphasize here that the nuclei are small, off to the side of the cell, and the vast majority of the adipocyte is going to be filled with this large transparent storage vacuole filled with triglycerides. And that's all we have for this recording. If you have any questions or comments, please feel free to post them in the class discussion board or shoot me an email. And as always, happy studies.